So today I want to talk about the mean, also known as the average, also known as the expectation, also known as the expected value of a random variable. It gives us a way of summarizing a random variable based on the average of all of the outcomes weighted by the probability of those outcomes. As always, we'll start with a story. The elder knew that the taxes collected from the members of the village varied widely. About 10% of the villagers could contribute 5 florins a year, while 40% could contribute 2 florins, and the remaining 50% only 1. What, the elder wondered, was the average amount of taxes that a villager paid? Consider a random variable x that takes on different values. The variable x could be like the taxes paid by villagers in the story, where the probability that x equals 5 is 0.1, the probability x equals 2 is 0.4, and the probability x equals 1 equals 0.5. Suppose that there were 1,000 villagers paying taxes x sub 1 up through x sub 1,000. The sample average of the taxes paid by the villagers would be x sub 1 plus x sub 2 plus etc. up to x sub 1,000, all divided by 1,000. Because of the probabilities assigned to each value of x, it is not unreasonable to believe that there would be about 100 that paid 5, 400 that paid 2, and 500 that paid 1. Of course, because the random variables are random, those would not be exactly the values, but close. If these were the exact numbers, say that villager 1 through villager 100 paid 5, villager 101 through villager 500 paid 2, and villager 501 through villager 1000 paid 1. Then the sample average of x would be 5 plus 5 plus 5 repeated 100 times, plus 2 plus 2 plus 2 repeated 500 times, plus 1 plus 1 plus 1 repeated 500 times, all divided by 1,000. Well, that makes the fraction 5 times 100 plus 2 times 400 plus 1 times 500, all divided by 1,000, and dividing the 1,000 through the numerator gives 5 times 0.1 plus 2 times 0.4 plus 1 times 0.5. This number is a weighted average of the possible outcomes. Each outcome is multiplied by the probability of that outcome, and the whole thing is then summed up. Define this number to be the expected value, or mean, of the random variable. Like the median, the mean is another example of a measure of central tendency, and only depends on the distribution of the random variable. Suppose the probability that x is in the set little x sub 1 up through little x sub n equals 1. Then the expected value, also known as the expectation, average, or mean of the random variable, is the sum as I goes from 1 to n of little xi times the probability that big X equals little xi. When u is uniform over little u1 up to little un, then this expected value of u is just the sum as I goes from 1 to n of 1 over n times u sub I. In other words, it's just the sample average of the u sub I. Now, indicator functions have especially nice means that connect averages with probabilities. For S an event, the expected value of the indicator of that event is just the probability of that event. Since the indicator of S is either 0 or 1, the expected value of the indicator of S is 0 times the probability that the indicator of S equals 0 plus 1 times the probability that the indicator of S equals 1. Well, the indicator of S equals 1 only if S is true, and that happens with probability of S. So really, all of probability can be considered a special case of expected value. The definition given works for when x only takes on a finite number of values, but what about distributions like the geometric, where the values could be any positive integer? Then an infinite sum is needed. Unfortunately, not all infinite sums converge. For those that do, the random variable is called integrable. Let x be a random variable with the probability that x is in the set x sub 1, x sub 2, etc. equals 1. Then consider the infinite sum. Sum as I goes from 1 to infinity of x sub I times the probability that big X equals little x sub I. If this sum converges, call the result the expected value of x, and say that x is integrable. Note that if w is greater than or equal to 0 with probability 1, then the sum as I goes from 1 to infinity of w sub I times the probability that big W equals little w sub I will always be either a real number or infinity. This leads to the following fact. A random variable w is integrable if and only if the mean of the absolute value of the random variable is strictly less than infinity. Of course, if a random variable x only takes on a finite number of values, it can only be as large as its largest value in absolute value, so it will always be integrable. If the probability that x is in a finite set, little x sub 1 up through little x sub n equals 1, then x is integrable. So now the expected value is defined for a discrete random variable, but how does that relate to the sample average from the story? For instance, if x sub 1 up through x sub 1000 are IID draws with the same distribution as x, and x has mean of x, how does the sample average x sub 1 plus x sub 2 plus and so on up through x sub 1000 divided by 1000 and the mean of x compare? Will they be close together? It turns out the answer to that question is yes, and is the subject of one of the most important theorems in probability, the strong law of large numbers. The strong law of large numbers says that given a sequence of random variables, x sub 1, x sub 2, etc., that are IID with distribution identical to x, where x is an integrable random variable, then the probability that the limit as n goes to infinity of x sub 1 plus x sub 2 plus up through x sub n divided by n equals the mean of x, the probability that that limit exists and equals the mean of x will be 1. There is a lot to unpack there, and here are some of the highlights. Because x sub 1, x sub 2, etc. are random variables, so are s sub n, which is the sum of the first n of the x sub i's divided by n for any n. Now the random variables x sub 1, x sub 2, etc. are IID, but the sample averages s sub n are not independent, since s sub n plus 1 uses a lot of the same x sub I values that s sub n does. Even though the s sub n are not independent, it is possible to say something about how they behave. With probability 1, they will get closer and closer to the numerical value of the mean of x if x is an integrable random variable. If the mean of x does not exist, it turns out that the limit will never exist with probability 1 either. Now the limit never existing includes the case when the limit is infinity. The with probability 1 part of the strong law of large numbers seems a bit weird. Recall that events that are always true have probability 1. However, you can have an event of probability 1 that isn't logically true. When dealing with an infinite number of possible outcomes, it is possible to have an event which is not logically true, but still has probability 1 of being true. It helps to look at an example. Suppose that D is the roll of a fair six-sided die. Then the mean of D will be 1/6 times 1 plus 1/6 times 2 and so on up to 1/6 times 6, which adds to 3.5. Hence, for an IID sequence of fair six-sided die rolls, the sample average will converge to 3.5. But what if every single one of my die rolls happened to be 2? Then every sample average, S sub n, which is the sum of the first n d sub I divided by n, will equal 2 as well. So the limit of the sample average will be 2, not 3.5. It is possible for the limit to not equal 2. But what is the probability that it actually equals 2? Well, we know the chance that every single die roll is 2 is 1/6 times 1/6 times 1/6 and an infinite number of 1/6. So we get 0. Another sequence where the limit is 2 is when d sub I is 1 for I even and d sub I is 3 for I odd. But the probability of drawing that sequence is also 0. There are an uncountably infinite number of such sequences where the limit is not 3.5 or does not exist. The strong law of large numbers says that the probability of all of these bad sequences combined is always 0, which is a very powerful statement. Now, some operators have the property that they are linear operators. A linear operator takes as input a vector and returns either another vector or a scalar. Now, if you have not worked much before with vectors or scalars, they form together what's called a vector space. Any two vectors can be added together to give another vector. A vector can also be scaled to give another vector by multiplying by a scalar. And these operations of multiplication and addition have to obey certain rules of commutativity, associativity, and distribution. In general, we say that script L is a linear operator if for all vectors v and w and scalars a and b, script L of a times v plus b times w equals a times script L of v plus b times script L of w. In other words, the operator should be able to be distributed over addition, and multiplication by scalars should be able to be pulled out of the operation. Now, you've seen linear operators before. For example, derivatives. Here, differentiable functions are the vectors and real numbers are the scalars. For f and g differentiable and a and b real numbers, the derivative of a times f plus b times g is a times the derivative of f plus b times the derivative of g. With integrals, here integrable functions are the vectors, and again real numbers are the scalars. For f and g integrable over the set A and little a and b real numbers, the integral over a of af plus bg with respect to the differential element of big A is a times the integral of f plus b times the integral of g. A similar result holds with limits. Suppose that a sub n and b sub n are sequences that both have a limit as n approaches infinity. Then for any constant c1 and c2 and r, the limit as n approaches infinity of c1 times an plus c2 times bn equals c1 times the limit as n approaches infinity of a sub n plus c2 times the limit as n approaches infinity of b sub n. But wait a minute. The strong law of large numbers says that the limit of the sample average equals the expectation with probability 1 when the expected value exists. So from the linearity of limits, the linearity of expectation follows. For integrable random variables as vectors and real numbers as scalars, the expected value is a linear operator. Note that there is nothing about whether or not the random variables are dependent or independent. Linearity works in both cases. Similarly, the derivative of f plus f is f prime plus f prime, even though the sum was of the same function. For example, suppose that x has expected value 3 and y has expected value -1. What is the expected value of 6 times x plus 4 times y? By the linearity of expectations, this is 6 times the mean of x plus 4 times the mean of y, which is 3 times 6 plus -1 times 4, or 14. Here's another example. Let u be uniform over the interval from 0 to 1, so u is a standard uniform. X is 2 times the indicator that u is less than 0.3, and y is 3 times the indicator that u is less than 0.6. What is the mean of x plus y? Well, even though x and y are not independent, the mean of x plus y is the mean of x plus the mean of y. which is 2 times the mean of the indicator that u is less than 0.3, plus 3 times the mean of the indicator that u is less than 0.6. Now recall that the mean of the indicator of an event is just the probability that that event is true. The probability that a standard uniform is at most 0.3 is 0.3. The probability that a uniform is less than 0.6 is 0.6. And so we get 2 times 0.3 plus 3 times 0.6, which is 2.4. Some distributions are symmetric. When a random variable x is symmetric around a value m, the expected value of x is also m. To be precise, first define what it means for a random variable to be symmetric around m. We're going to say a random variable x is symmetric around the real value m if x minus m and the negative of the quantity x minus m have the same distribution. For example, if x is uniform over 1, 2, 3, and 4, prove that x is symmetric around 2.5. Well, x minus 2.5 will be uniform over negative 1.5, negative 0.5, 0.5, and 1.5. While if we take the negative of that value, that's going to be uniform over 1.5, 0.5, negative 0.5, and negative 1.5, which is the same set. It's just that the elements are written in a slightly different order. In general, uniforms have the following symmetry. If x is a uniform random variable from the integers a up through b, then x is symmetric around the quantity a plus b divided by 2. Why is symmetry useful? Well, if x is an integrable random variable symmetric around the value m, then the mean of x has to equal m. Now the reason for that is that the expectation of x minus m will equal the expectation of negative x minus m. So if I take one and subtract it from the other, I'm going to get 0. So that tells me that 0 is the expected value of x minus m minus the quantity x minus m. But I can simplify that to be the mean of 2x minus 2m, which is 2 times the mean of x minus m. Solving for the expected value of x completes the proof. Now, symmetric random variables with densities have symmetric densities. In other words, if x is a random variable with density f sub x of little x symmetric around m, then the density of big X at x minus m equals the density of big X at m minus x. The density of x minus m is the density of x at x minus m, and the density of negative of x minus m is the density of x at m minus little x, and so the result is shown. Note that when the mean of the absolute value of x exists for x discrete, we call the random variable integrable, not summable. That's because the sum can be written as an integral with respect to counting measure. Recall that the sum over little w of w times the probability that big W equals little w is the same as the integral over little w of little w times the density of big W at little w with respect to counting measure. This integral formulation will be helpful when extending the idea of expectation to continuous random variables. So that's how you calculate the mean of a random variable. Of the 3 measures of central tendency, the mode, the median, and the mean is by far the most important, and we'll expand on the various ways that the mean can be applied in the chapters to come. See you next time.